Our next chapter is about electromagnetic waves. And before we get into that, I thought in this lecture 9A2, I'll give you a brief introduction about waves, part of which you might be familiar with from your school days. Before, so let's take a compass for the whole chapter that we're going to do. Okay, what are the things that we're going to do in this chapter? So it's important to have our way through. So compass for the journey through this chapter, which will be probably for 1.5 or maybe 2 weeks on electromagnetic waves. And so I'll give you an introduction to one-dimension waves. And then we'll do Maxwell's equations, how Maxwell's equation gave rise to EM waves, the crowning achievement of Maxwell's equations. Okay, as said, God said that let there be light, and there was light. Electromagnetic waves are, of course, a whole range of phenomena, but we'll do it in vacuum to start with. Then we'll get into dielectric medium and into conductors, which is a lossy medium. And in both in dielectric and conductors, we'll do transmission, reflection, and so on, reflection and transmission at the, especially at the interfaces of or is a boundary between two media, and there could be lossy, and then absorption would occur. Okay, absorption, and a phenomena of dispersion you're familiar with in terms of prism, or let's say rainbow. So we'll get into that. Electromagnetic waves, of course, is you remember the span of electromagnetic waves is from very small wavelength, that is gamma rays, to X rays, to ultraviolet, then visible light, then microwave, AM, FM, 3G, 4G. Okay, then you get into RF, and so on and so forth. So the range of phenomena of electromagnetic waves is very wide. So this chapter is supposed to become the basis of all that, and interaction of light with matter to some extent. So there are two ubiquitous phenomena, okay, in ubiquitous presented everywhere, in physics and of course in nature, and those are vibrations and waves. You would have done vibrations in physics 102 a lot. Okay, vibrations or oscillations, and waves. Vibrations, the typical model that comes to your mind is the mass spring system or a pendulum. Okay. And the signal of especially the simple harmonic motion, is that the second order in time is proportional with a negative sign to with a positive. This omega square is a positive quantity, and the variable itself. Okay, that gives rise to simple harmonic motion. And the solution we seek in terms of complex exponentials, you must have done this a lot in physics 102. This preponderance of vibrations and oscillations are everywhere in all branches of science and engineering, everywhere in nature. Why is that? Because most things are at the stable equilibrium, and then any motion around the stable equilibrium, okay, and that is the minimum of the potential energy, gives rise to oscillation because it tries to restore its motion. Okay, and that is why if you have a minimum energy minimum, this minimum can always be a half kx square type. Okay, at the time. So if there is motion around that, it gives rise to simple harmonic motion, and that is why everywhere in nature you will see vibrations, oscillations is a very common phenomenon. In physics 102, you would have done two sets of major problems. Once where the potential energy is like this, okay, or is the inverted ball, the potential energy. In that case, the solution is not is not imaginary exponential, but a real exponential, which gives rise to cos hyperbolic and sine hyperbolic solutions. Okay. In this case, it gives rise to cos omega t and sine omega t solutions. So these are the two major chunks of problems that you would have done. Now let's come to waves. The most familiar wave that we know is a wave on a string, on a taut string with the tension. And there, if I produce a shape, then the shape travels, okay, along the string in time. Okay. So this is one string. The other wave that you are familiar with is take a sling, and if you make it vibrate along the longitudinal direction, then a wave goes. So this we know is the transverse wave, meaning that the displacement of the string is perpendicular to the direction of propagation. And here in a sling, the disturbance travels in the same direction as the sling is vibrating, and that is a longitudinal wave. So there are two major types of waves, and they follow the wave equation. You might have seen it earlier, but this now has a partial differential equation in space, second order in time, related by the velocity of the wave. Okay. We will, in a way, will derive this or make it plausible rather than derive. And the solution is, of course, both x and t. We'll get into that. And there's a wide variety. There's strings, sound waves, a longitudinal wave, electromagnetic waves we'll deal with. Even Schrodinger is a wave equation, but this is not the equation for Schrodinger. This is in Schrodinger equation. If you have already started doing it in chemistry, or you wouldn't have done it in physics so far, but in chemistry or so, then this is first order in time. Okay. And except that it allows for complex solutions. Okay. In our case, the real life world, and so we'll look for real life solutions in waves. But it's present. Waves are present in every discipline of science and engineering, and everywhere in some sense. One of the main characteristics which distinguishes between vibrations and waves is they're related, because waves quite often arise from vibration. A sound wave comes from a vibrating tuning fork. Okay, so and so there might be or a oscillating dipole gives you radiation electromagnetic wave. So they're related, but they're very distinct, because vibrations or oscillations are localized in space. Okay, whereas the essential nature of waves is that the disturbance is carried across space, so it is non-local. That is difference. So let's get into the waveform, the form in the simplest case, in which it is a shape preserving disturbance, okay, with a constant speed. That is the simplest case. There can be many modifications in different disciplines and different situations, but we will worry about this simple case at the moment. Okay, so let me show that this is, let's say, one shape, and after some time, so this is f, and so whatever with this could be displacement, this could be something, some value, but in the shape of the in space, in as a function of z, let's say. And then after so f of at z t is equal to 0, this is the shape, and then it travels with velocity v, let's say in the plus z direction. And then after some time, this f z of t. All right. And so f z of t, you can think of that this is it was the same exactly z minus vt back in space at t is equal to 0. So fzt is exactly equal to fz minus vt at t is equal to 0. That is this is how the shape is preserved. So this combination of z minus vt is important for waves, because it says that at time past t, the shape that I am having now was the same exactly, because I've been traveling with velocity v, and in a space where I was in z at z minus vt, the space was exactly the same. Okay, so that is the idea of shape preserving and at constant speed. Now, let me say that this shape I can describe at g of z. Okay, Z is the direction. So I can write down this fz of t as g z minus vt. Now it can be thought of as a wave of fixed shape traveling in the plus z direction. What I've shown you, traveling this plus z direction with a speed v. Now, so this combination is very special. Okay, z minus vt for wave motion. I want to re-emphasize that. If you want a sort of a definition, in physics we don't worry about so much about definition, but the description of waves, then the classical traveling wave is a self-sustaining disturbance in a medium which moves through space. What moves through? Disturbance moves through. May not be the particle itself. Okay, there may not be actual material transport, but there is transport of energy and momentum because of the transport of the disturbance. That's the wave class of phenomena that we are describing. Let's take the most familiar example of a wave on a stress string. So that's you are probably already familiar with it, but I'll go through it quickly because that gives us the opening gambit, so to say. Okay, so in a stress string, if you consider a small fraction of the stress string, okay, a long string under tension T with a small distortion meaning theta and theta prime are small, and theta is the display is the angle at z, and z plus delta z is theta prime. Net transverse force acting on this segment, okay, we can write down. So the weight is of course balanced by cos theta, okay, but the transverse segment is t sine theta prime minus t sine theta, okay, here, and minus t sine theta here. Now if theta and theta prime are small, for small distortions, that is, I can write down delta f is t tan theta prime. I can sin theta prime is equal to tan theta prime and tan theta. And tan theta prime is like a slope here. Okay, that is the whole. So del f by del z at z plus z tan theta prime minus del f by del z at z. And that I can approximate it to, okay, because this is already first order differential. This first order differential, small differential over delta z, that is second order. So second order del square f by del z squared delta z into t. So that is the delta f, okay, in the transverse direction. Now that is in terms of the shape of the distortion. But how about Newton's law, second law? Newton's second law will tell us is that del f, the force is of course, let mu be the mass per unit length into delta z, that's the mass for this little segment, and the acceleration, that is del square f by del t square, that's the force. So and hence I can write down now, so I have gotten delta f in terms of del square by f del z square, and I got delta f in terms of del square by f delta t square. Mu z, delta z and delta z cancel, and hence del square by f by del z square is equal to mu by t coming from here, mu by t del square f by del t square. Mu is mass per unit length, t is the tension. So this distortion then obeys this equation, and this I can write down is del square f by del z square, this quantity as 1 by v square, where v is equal to root over t by mu. Okay, this is for a string, particularly for a string. So that is strip, and hence I can say the small disturbance on a taut string under tension satisfies this equation. We can generalize that for all such waves, especially in one dimension. So general one-dimensional wave equation. Let's so that is what it would be. We have already seen in case of the stress string, but this will be a lot more general. And we now know that it admits solution of the form in ways that particular combination is there, z minus bt. Okay, because the shape is repeated, as it keeps moving with velocity v. And so if there is any pattern like that is moving v, then at later time it reproduces exactly the same pattern. Okay, so remember we're talking about shape preserving constant speed waves. So then I can, this shape I can write down as g z minus vt, and this I can define as g of u. Okay, so u is z minus vt. As I said, this is the most special combination, and let's keep that at the center of our focus. And now let's look at the del f by del z. Then I can write down, this is g is only a single variable, so dg by du. And of course, I have to take the partial derivative of del u with respect to del z. And what is that? That is 1. So del f by del z is dg by du. If I do the same thing with del f by del t, then dg by du, then partial derivative of u with respect to time, that gives me minus v here. So minus v dg by du. I can go ahead, and I know I'm looking for second order differential equation. So I can do second order, then del square f by del z square, del by del z. So del by del z is just one more differentiation in this case. Okay, so that you end up, and del u by del z is still 1. So d square g by du square. Okay, now let's come to what happens to the second derivative in this case. So del square f. So every time you differentiate del by del t, you pick up a factor minus v, and hence this will be and of course one more differentiation. Okay, so del square f by del t square is picks up minus v again, del b del t, and del v minus v, and d square dg by d square, and hence it becomes del u by del t is minus v again, minus v is v square, so it is v square d square dg by du square. This is only d square dg by du square, and that gives us the wave equation. So del square f by del z square is del square f by del t square divided by 1 by v square. The general argument. Okay, so and gu can be any differentiable function. Okay, and if it propagates without changing shape, then it must satisfy this equation. That is the claim. Let's look at some of the properties. This looks like a linear equation. The equation is in f. Okay, and hence the most general solution would be a combination, because it's a v square. It allows for something which is minus v and plus v. Okay, so if it is plus v, then it is going in the plus z direction. That is, this minus vt here. And if this v itself becomes minus, then it becomes g plus vt. Then it is traveling in the in the left direction. It is in the minus z direction. So most general solution of this would of course allow for a wave traveling to the right and wave traveling to the left. So fz of t would be gz minus vt h z plus vt. So that's the most general solution. This is the most general one-dimensional wave equation. We would focus on what is called the sinusoidal waves, or let me call it harmonic waves. Okay, that is either sine or cosine. They are the same. They have only a phase constant that is different. And of course, that wonderful God's gift, okay, is ei theta, which includes both sine and cosine. Okay, so the imaginary part is sine, the real part is cosine. So in one simple, and the algebra of E of I theta is going to be very simple, and hence we are going to consider that. So many functions can be periodic, both in space and time, but okay, only sine or cosine, and hence ei theta, can have a wavelength or a frequency in time and wavelength in space. So sine and cosine are the only true waves. Okay, sine, cosine, and their combination, let's say ei theta. This is the only pure wave. We can associate a lambda and omega waves. So, but typically we don't. If there a one-dimensional, the solution can be involves constants, which a is the amplitude of the disturbance. Okay, then we'll define k. This is traveling in the plus z direction and with a velocity v, and it can have some time delay at what point it crosses z is equal to 0. Okay, so that is a phase constant that can be there. So this is the most general solution. And because of this delta, you can also write down in terms of cos and sine. Okay. Now, I can write down, I can take k inside, k is kz minus omega t. So that means omega is k into v plus delta. So this is the most familiar form in which we're going to use the one-dimensional wave equation. So, and this is can be written as the real part of this complex, this cos a I kz minus omega t delta. Now this part is, that's why it's called the phase, okay, because it's an argument to sine or cos, and this is called a phase constant. The whole thing is, of course, is a phase. So a wave solution has an amplitude, that's the amplitude of the wave, and there is a phase which is, changes with space and time. This is what actually captures the periodicity of the wave functions, variations within in space and time. And this is a phase constant, okay, which you can set it to 0 for convenience by setting your reference origin. Uh, so A is the amplitude, which is the maximum displacement from equilibrium of the quantity of the disturbance that you are worrying about. K, it's not a vector at the moment, but we'll soon make it a vector in the next lecture. So let me call it a wave vector. This is 2 pi into wave number. Wave number is simply 1 by lambda. That is number of wavelengths per unit, number of wavelengths in unit length. Okay. So that is wave number, and multiplied by 2 pi, and that we'll call it, I'm still calling it a wave vector because k can be both plus and minus. Okay. So I'm beginning to call it a vector, though I have not put a vector sign here. Okay. So let's define k is 2 pi by lambda. Lambda is a positive quantity. Okay. But k can be can be plus or minus, as we'll say. So there's a possibility, instead of lambda, we use k because there's a possibility of making it a vector, okay, later. So there are other advantages. For example, for a wave traveling in a minus z direction here, I need to just switch k to minus k. Okay, e to the cos minus kz minus omega t. Okay, so cos is of course an even function, and so that the shape remains the same, but the velocity it's moving in the minus k direction. We also, from modern physics, are familiar with the relation that the momentum associated with a wave is h by lambda. I'm saying the use of k, the significance of use of k, and I can write down in terms of h cross. So this 2 pi by lambda. So, and the momentum then becomes h cross k. And of course, momentum is a vector later, right? And hence, the possibility of using lambda, of course, is the main feature, but using it in along with direction, the k is a lot more convenient instead of lambda. Instead of writing down simply 2 pi by lambda everywhere, we also include a direction into it, and that is why we use k in our wave descriptions. Of course, we are familiar with time period from oscillations. This is the same time period, and nu is frequency. So this is the number of oscillations per unit time. This is, and the angular frequency, we know, this is the radians swept per unit time. So omega is, of course, angular frequency. We write down, this is the most convenient expression for waves, k and in terms of k and omega. Omega is 2 pi nu, and I've already said that if I brought in k inside, then this becomes omega. So omega is k into v. So omega is a function of k. This is a very simple function here, but later you can see that more complicated waves can have omega complicated functions of k. So in other way to remember is v is, or the phase velocity is omega by k. So our focus is on sinusoidal waves only, and especially in their complex representation for convenience. Okay. So fzt is, this is is sinusoid, either sine or cos. And if I set delta is equal to 0, then if I did not set it equal to 0, I can make f a complex wave. zt. Then I define a complex wave as A, then amplitude I make complex. Now amplitude A, EI delta is now as a part of the amplitude, and that is why it's a complex number. So amplitude is a complex number, so this delta has been absorbed here. So this is a definition of a complex wave. It's very convenient, okay, for ease of doing the maths with these objects or these waves. I think we define a complex wave where the amplitude is complex and is A EI delta. Okay, so or or A cos delta sine plus I A sine delta. All right. So the imaginary part. So this makes superposition because it's a linear equation, and hence, if there are two solutions, then they can be, or there are different waves. I can add waves. Okay, and adding waves, or suppose there are many wavelets. Okay, and then I want to add them, and then superposition becomes very easy if I define a complex wave, because in that case the complex amplitude is simply gets added up. Okay, now especially with the same k, the same wavelength and same omega, especially for that case. So for any well behaved, I mean, all physical waves are well behaved. Okay, since they physically occur, we'll call them well behaved. Wave shape, one can always construct it by superposition of sine and cosine waves of different wavelength and frequency. Who said so? Fourier. Okay, and you are going to learn Fourier analysis, Fourier transform, and Fourier analysis in a great detail in your maths course, and you're going to use it in many different courses in future. All right. So, but the point in this course, we are not going to use it in this course. Okay. But the point is that any complex shape, okay, or complex wave can be made up of component superposition of many different sign of different wavelengths and frequencies. Okay, and hence, if you want to study waves, it is enough to study how harmonic waves or sinusoidal waves, the sine and cosine, actually behave. Okay, and that is why we in this course will only focus on sinusoidal waves. Okay, hence in this course we will only consider sinusoidal waves. In principle, that should be enough for getting to know how any wave behaves. All right. The superposition, the complex superposition, this is the complex A, and so I can integrate from all possible wavelengths. Okay, and of course, k is a function, omega is a function of k, in our case in kV, and hence the superposition I can just by integrating, the only thing that for each wavelength and that I have chosen to integrate, there is a different amplitude. So if I choose the wavelengths and amplitudes properly, I can make any wave. That's what Fourier theorem says. Okay, and you will be doing it in great detail. I'm not going to use Fourier's analysis in this course. But remember, k can be both positive or negative, and lambda and omega are always positive. And omega is a function of k, is called dispersion relation, and y and all that. We'll study that towards the end of this chapter. Omega is a function of k. This is being integrated over k dk. Now, polarization. Let me give a quick introduction to polarization waves. So that could be transverse waves, we know, and I have already said that in the first slide itself. The direction of propagation is perpendicular to the displacement. Okay, but that could, and here, for example, it is the displacement is oscillations occurring in perpendicular, and whereas the wave is actually traveling perpendicular to the oscillatory motion. Okay, that is called a transverse wave. We know that. And in longitudinal wave, the direction is parallel. Okay, and that is especially for, let's say, sound wave. This is for electromagnetic waves or string waves. So the direction is itself is parallel to, this is oscillating in this direction, and the wave motion happens in the same direction as it oscillates, and that is longitudinal wave. In transverse wave, we can have polarization. Transverse waves can get this polarization has nothing to do with the polarization that you did in dielectrics. Okay, this is orientation of the oscillations with respect to the propagation direction. So if there is one propagation direction, then there are two perpendicular directions directions which are perpendicular to the direction of propagation, and hence the oscillation can occur in those two, and hence we call that two independent polarized states. For example, if this is going in a z direction, then there is a vertical polarization which will be in I direction. Okay, or horizontal polarization where it will be in the j direction, in the y direction. Okay, so if let's say, see, this is my vertically polarized. Okay, it's traveling, or it's oscillating in the along y direction. Okay, but it's traveling in v. So this is one polarized state, and this is another polarized state. Polarization is a state of the wave. Okay, which determines the oscillation as direction as compared to the direction of propagation. That could be in general a possible polarization in which, for example, the polarization direction is n hat, and which let's say is theta with respect to x. Okay, the direction is in this direction, but the polarization is in some arbitrary direction, which is still perpendicular. So n dot k. So I can write down that amplitude k, but the polarization vector is pointing in the n hat direction. Okay, where n dot k must be 0 because the n must be perpendicular to the direction of propagation. And the example that I have taken here, the direction of propagation is in z direction, and hence I can write down the polarization unit vector in terms of cos theta I and sin theta j. Okay, uh, and so any transverse wave can be expressed as superposition of two independent polarizations. For example, I can write down f z t as the complex amplitude cos theta I and complex amplitude sin theta j. Okay, so basically I have taken n resolved into I and j direction and taken it here. So any transverse wave can be expressed in terms of two independent polarizations, okay, in the two different directions. It will be useful to us in later chapter. So let's give a quick summary. Summary is the whole point was to familiarize you with one-dimensional waves, and the general form of the wave equation, we know. Okay, it's a second derivative in space and time for waves that preserve shape and move with constant speed, moving with constant speed. No source terms are there. Okay, it's a homogeneous term. That is, if you take the two terms on the same side, then this is a differential equation: del square f by del z square minus 1 by v square del square f by del t square is equal to 0. Okay, so and such a differential equations with 0 is called homogeneous equations, and there is no source. Okay, like in Maxwell's equations, you had source of rho or j. Here is a sustaining motion without any source. Okay, and it's a linear equation. I have already discussed that. The functions of linear in z plus minus v are general solutions of the wave equation. All right, that we have also seen. The wave vector, I'm calling it wave vector k without putting an arrow, and angular frequency omega are the two most significant parameters which characterize the sinusoidal waves. Okay, and we said that any general wave can be made up of sinusoidal waves. Okay, and that is why the k and the choice of k and omega as a function of k is important. So we will focus in this whole chapter only on sinusoidal waves, because you can get any general wave from superposition of sinusoidal waves. With that, we'll now get into electromagnetic waves, and I hope you It is just a recalling the things that you have probably heard or familiar at one place before you get into the electromagnetic waves proper. Thank you.